RL Circuits 3. Now we derive an equation for the falling time-varying current through an RL circuit, picking up where our previous work left off. Now, what was that previous work? In an earlier video, we flipped the switch to point 1 here, and we derived an equation for the current changing with time as it went counterclockwise here around the left side of the circuit. Now we're going to flip the switch over to point 2 and figure out what's going on. It says right here at this point, the battery will no longer be a part of the circuit, and you can clearly see that. Once we flip that to point 2, there won't be any battery involved. At the instant the switch is thrown to point 2, there would be an EMF induced in the inductor that is directed in which direction? Well, the current through the inductor is going down towards the bottom of the page here, and remember, inductors don't like change. So as soon as we shut off the battery, as soon as we turn off the juice, if you will, this inductor doesn't like that change. So it's going to wake up from its slumber, and it's going to attempt to keep that current going by having an EMF that's induced towards the bottom of the page. Starting at point 2 and traveling counterclockwise, let's write the Kirchhoff's loop equation for this situation. I've given you a hint here. Both terms on the equation's left side should have negative signs in front of them. When we flip this switch over to point 2, we're going to go all the way around the circuit. So let's start at point 2, and the first thing we run into is a minus IR. And then whenever we go through an inductor, we have to say minus L di dt. And then we're back to our starting point, which was point 2, like that. Let's manipulate this equation, and this is the first step in solving this differential equation. We notice that it is a differential equation because it has a variable I, and it also has a derivative of that variable I. Let's put dt and di in numerators with only I stuff on the right, and let's put the negative sign on the left. If we manipulate that, we're going to end up with minus R over L dt is equal to di over I. Hopefully we're okay with that. You check it out, but it comes out to be that. I don't want to waste your time. All right, we're going to rewrite part C here, showing that we intend to integrate both sides of this equation, with the left side from t0 to some later time, and then the right side is going to be initially some value of current, because initially there is some non-zero current in there, to some later amount of current. So here we go. We're going to integrate from t equals 0, some later time t. Remember, whenever we flip the switch, time starts over again, which is why it says time 0 here. Minus R over L dt. And we're going to integrate the right side from that initial current value, which, by the way, that initial current value right there, in our previous video, we decided that it was just the voltage of the battery divided by the resistance of the circuit. So numerically, that's what that is. To some later current, I, di over I. Let's integrate this. Well, when we integrate the left side and we put in the limits, that's just going to give us RT over L. And when we integrate the right side, hey, no need for U substitution this time. We're just going to get the log of I. You can put parentheses, or if you want to put absolute value signs, that's okay. Now, the whole point here has been to get an equation for little I, which could be written I as a function of time, but we just didn't put that in there. So now we need to e to the both sides. So I'll show a little bit of work here. We're going to e to that side, and when we e to this side, it ends up as I, I'll put the t in there now, over I naught. When we solve this for the time varying current, we're going to get I naught times e to the minus RT over L. A long time ago, maybe you remember, we said that if you have an equation that goes e to the minus something without a 1 minus in front of it, if it's just e to the minus something, then that is a falling graph. And so we said earlier that this I naught is numerically equal to E over R for the battery, right? That's the battery voltage divided by the resistance of the circuit. There you go. That is the equation. Let's finish by drawing some graphs of resistor voltage, inductor EMF, and current. When we started this whole thing, when we flipped the switch to point 1, the inductor fought the battery right at the first instant. And then that inductor quit fighting. Because the inductor fought the battery at the very first instant, there was no voltage drop across the resistor. And why is there no voltage drop across the resistor? Well, there was no current at first, right? This was when we had the switch at point 1. And this asymptote here is that E over R value. That's when we first had the switch to point 1. Now, when we flip it to point 2, the inductor wants to keep the current going. See, the current is at this level right here, E over R. And remember, the inductor wants to keep that current going. So at that first instant, it is able to do that. But then that current is going to drop off like that. And that means that the voltage across the resistor is going to be proportional to that. So it's going to drop off like that, where that is numerically equal to the voltage of the battery. And where is that voltage coming from? Now it's coming from the inductor that is trying its best, but ultimately failing, to keep that current going